In this second video that's for and in support of high school teachers of geometric algebra, we'll discuss a common objection to geometric algebra, which is the adding of scalars and bivectors. By the end of this video, teachers will have the background to give a convincing high school level answer to a question and objection that students are likely to raise, and indeed it's raised commonly by physicists and mathematicians. As just a brief review of geometric algebra, it's a highly effective extension of vector algebra and calculus, for lack of a better short description, and it can be introduced effectively at the high school level. And indeed, there exists a LinkedIn group that is dedicated to that very purpose, and I'll put the link in the video description. One of the members of that group, a Professor Philippe Hénin, has pointed out quite correctly that, or the need to convince high school teachers of the advantages that GA has for teaching STEM subjects. And of course, as part of that, we need to provide teachers with background to give convincing answers to the students' questions. A previous video discussed the question, well, regarding multiplication of vectors, where would anyone get such an idea in the first place? In this video, we'll address the objection that you can't add unlike things, specifically scalars and bivectors. So what do we mean by that? Well, let's review what scalar and outer products of two vectors are. The outer product is what gives rise to what we call the bivector. So let's just draw two vectors here, A and B. Now, to discuss the dot product, the scalar product, I'm just going to deal with the dot product of A with B's unit vector. That's all we'll need here. So the direction of B's unit vector would be about like this. And what we call A dot B, or the scalar, or the value of the scalar product, is the length of A's projection upon B, on the direction of B, I should say. Now, we could say more about that and the algebraic sign in that, but I'll leave it for that, or I'll leave it at that for now. Anyway, this product is a scalar, and its magnitude is that length. The outer product is quite different. To form or to represent it geometrically, we'll take A, and onto that we'll stick B. And now we'll form the parallelogram. The magnitude of A wedge B, which we call, well, the bivector, is an oriented segment of this plane that contains the two vectors. The magnitude of this bivector here is nothing more than the area of that parallelogram. This also has, or what we call its orientation, I'm going to erase here for just a second. What we call the orientation refers to the direction of the turn that we make when we go from A to B. So the orientation of this bivector is a sense of rotation. It would be in this sense. Now, an important thing to recognize here, and again I'll erase for just a bit, is that the area of this parallelogram that we just described is also equal to the area of the rectangle that would be formed, or that would have as one side A, and as the other the component of B that's perpendicular to A. So the dot product of the two vectors captures information about their parallel aspects, or the component of A that's parallel to B. The cross, or the wedge product, I should say, the wedge product captures the perpendicularity of the two vectors. From these two pieces of information, we can solve a lot of different problems. So that's all nice. What's the objection? Well, the way that we combine those two pieces of information is in what we call the geometric product of the two vectors, A and B. And here is our information about their parallelity and their perpendicularity, and the operation by which we combine them we represent by that symbol, and we call it addition. So the operation is fine. There's no problems with it. The problem arises from the use of that name and symbol, which raises certain expectations. This is a good time to explain to students that, okay, there are a whole slew of different operations called addition upon all sorts of objects. For example, vectors, matrices, fractions, real numbers, you name it. And we can't expect all of those different operations to all have the same properties just because we call all of those operations additions and represent them by this same symbol here. So we'll continue on here. Back to the objection. Well, all right. In all these other additions, for example, matrices with matrices, vectors with vectors, we add two things of the same type, and we get the same type of thing out of it. The sum of a vector with another vector is a vector. The sum of a matrix with another matrix is a third matrix, etc. Well, here we're adding a scalar and a bivector, so a pure number and a chunk of a plane, an oriented chunk of a plane no less. We're adding things that are unlike. Well, from all the expectations that this symbol has raised in the minds of students, this is just outlandish. It's absurd, and you'll hear physicists say the same thing. So there are unsatisfactory answers given to this difficulty. One is, well, just go ahead and add them. Well, you can't just do that. Not all of these additions have the same properties, so you can't just say you're going to add them, because the additions may have different, or the different properties that we call addition can have different properties. And others say, well, it's like making a salad. Well, all right. The analogy is that in a salad you throw things of different types and you come up with something good, even while the items you threw in there maintain their own identities. We can't give that kind of answer. We teach math so that students will learn to give good answers and to recognize what a good answer consists of. So if we want students to develop that kind of capacity, we have to model it for them ourselves. Another objection that we sometimes, or another answer I should say, that we sometimes get is this one, that, well, this is a whole new aspect of the addition operation, as if there were some grand encompassing addition operation, and that by writing the symbol plus between a scalar and a bivector, we've discovered some new aspects of this grand all-encompassing addition operation. Well, that just simply isn't how this came about. So we can't give that kind of an answer. We need to show, or the students deserve better from us, and so we have to give it to them. So those answers don't do justice to the inventors of geometric algebra, and by giving that kind of answer, we miss an opportunity to deepen and broaden the student's understanding of math. So the other part of this, of course, is that the objections to that term are quite reasonable. Not to the operation itself, but to again, the use of that term raises certain expectations in people's minds. One of the ways in which this addition is different from others is that it doesn't have the closure property. Again, vectors have a closure property. You add two vectors to get a vector, etc. That's not what happens when we add scalars and bivectors. We don't get, or we get something that's neither. The other thing that's odd about this addition is it will morph into others in use. And that's not a problem. It's actually a feature of geometric algebra. It's not difficult to understand, but we need to be clear with the students about what's going on. Otherwise, we miss a learning opportunity and we can't expect them to really come to understand all this. So, to help give an answer, or as an answer that is at a high school level and the students, I think, will find acceptable, let's consider a two-dimensional case. We'll have a scalar alpha and a bivector b. Now, as we showed earlier, a bivector is a section of a plane. Now, when we combine those two pieces of information, we discussed earlier the kinds of information that are encompassed here, we form this sum. Well, okay, so what happens? Well, if we multiply that sum by a vector, it morphs. And what do I mean by that? Well, okay, in the two-dimensional case, we are operating within a single plane, so that vector is going to be perpendicular to the plane, and b, this bivector, is just a chunk of that plane. So b and v are parallel. According to geometric algebra, the product of a bivector with a vector that is parallel to it is, well, I'll draw something here quickly. Let's say that's v, the vector. What bv will be is a vector perpendicular to the original v and either expanded or contracted. In either case, what we get out of that is a vector. Alpha times v, of course, is another vector. So what has happened here? Well, by multiplying this sum by a vector in the two-dimensional case, we get another addition here, which is just nothing more than this familiar addition of vectors. So this addition of scalar and bivector has morphed into vector addition. Why is this useful? Well, that's what we rely upon when we solve for an unknown vector u in terms of a known vector v. How do we go about doing that? Well, what we do in practice is, first, from the givens in the problem and from the various physical laws, we then, by fair means or foul, determine this scalar u dot v. We can do that from the givens and the physical laws without needing to know u itself. Similarly, we can find this bivector without needing to know u itself. Now we form the geometric product of u and v by adding this scalar and this bivector. So we come down here to having uv, the geometric product. Also in geometric algebra, every vector, in this case it'll be v, has a multiplicative inverse, which is nothing more than the vector itself divided by the square of its magnitude. So what we will do then to find u is we'll multiply the geometric product uv by the multiplicative inverse of v. Now in geometric algebra, the products of vectors are associative. So instead of associating u and v here, I'll associate v with its own multiplicative inverse. Their product is just the number 1. U times 1 is u itself. So formally, this is how we go about finding u. What does that look like in practice? Well, this is where the morphing comes in, or where it's useful. Again, from givens and physical laws, we can find, or we will have found this scalar and this bivector, and their sum is u times v. We multiply it by multiplicative inverse of v. And what's that look like on the right-hand side? Well, what we're going to do here first is write the multiplicative inverse of v according to its definition, which is v itself divided by the square of its magnitude. So this is magnitude of v times magnitude of v, and we're going to take one of those factors, that is the magnitude of v, and distribute it within this sum here. We'll write that more neatly on the next slide here. And what do we get? Well, a vector divided by its own magnitude is nothing less than its unit vector, and we have 3 of those here. So we still have the sum of a scalar and a bivector, but now we're going to multiply here, and this multiplication does distribute over the sum. But when we do this, again, this sum of a bivector and scalar morphs into a vector sum. This is a vector parallel to v, and this is a vector perpendicular to v. And we'll draw that more nicely in the next couple slides here. Here I've just rewritten this for reference and to guide us. Let's say this is our vector v, and this is a unit vector of that same vector. Again, we will have found this scalar. We multiply it by the same vector v, and let's say that's the result. And the product of this bivector and the unit vector v is this thing. So what does this tell us we do? Well, this is now a vector addition. Nice old familiar vector addition. So that's the geometric representation here of what's going on with this morphing of the sum, or this original sum of a scalar and bivector, into just a vector sum. So, in summary, high school teachers are indispensable to the wider adoption of geometric algebra, and teachers will need to be equipped to give convincing answers to the students' questions. In this video, teachers have seen, I hope, a convincing high school level answer to a question or objection that students are likely to raise. Namely, how can you add a scalar and a chunk of a plane? And as I mentioned earlier, this LinkedIn group is devoted specifically to helping teach geometric algebra at the high school level. We have members who are subject matter experts in geometric algebra. Others are teachers at the high school level or other levels. And some are indeed high school students themselves who have become interested and would like to know more about this. And their feedback on the materials we develop, the feedback from the students themselves, is invaluable. So I hope you will all consider joining this group, and thank you for your time.